Hello and welcome to Talk Julia. My name is David Amos.
And my name is Randy Davila.
So Randy, last week we kind of started a plunge into machine learning with Julia. We talked about the reinforcement learning.jl library. And this week we wanted to dive into Flux.ML, which is I think kind of more the standard machine learning library you think of when you're doing machine learning, not reinforcement learning. And
right.
So Flux describes themselves as the elegant machine learning stack. And I think, with what we've seen over the last week going through it, I agree with that description as being elegant. And it's 100% pure Julia, which is kind of a dramatic change if you're used to doing machine learning in Python, right? And you're coming to Julia in Python. A lot of every machine learning library I know of is not written necessarily in Python. It's in something like C++ or things like that, and it's being wrapped. There's a wrapper for it in Python, so you can call those things. But Flux is 100% Julia all the way down, which means for someone like an end user that maybe isn't familiar with C++ or whatever language they're writing, like the Python machine learning libraries in, then you can go into the source code and really understand like what's happening behind the scenes, right? And how to customize it maybe, or learn, just how it's working, which is really nice to just be able to go into the source code and see, well, how are they doing it? Like how is this actually working, and not have to, try to understand a language maybe you're not familiar with.
Right. That on top of the framework that they've chosen to design for these types of tasks really makes it accessible, right? When you look at how the API works, it works how it should, if that makes any sense.
Yeah,
at least from a mathematician's point of view, right? It like many things in Julia, Flux.jl really pokes at the mathematician in me. Is like, learn more about this because it's the right way to do it.
Yeah, it's, when you're reading code that's written using Flux, and let's say you're following along or you're learning machine learning from a more theoretical standpoint, you look at the Flux code and it just kind of looks like what you're reading about, right? There's it's really easy to translate between the theory and then what's actually going on in the code, which makes it, I think, just really simple to understand like what Flux is doing and what's happening with it. So it's got some nice features. And for example, this compiled eager code is a nice one. So it provides you a single intuitive way to define models, just like mathematical notation, kind of going back to what we were saying. And then Julia transparently compiles your code, optimizing and fusing kernels for the GPU, for the GPU for the best performance. It's really performance oriented, and you're getting all of that. And then the differential programming is something that's really cool about Flux as well. So it supports existing Julia libraries that are differentiable. So differentiable meaning like you've got like differentiable functions and things like that going into it. So you can incorporate all that stuff directly into Flux models. And that is something that, well, I guess to be honest, I don't have a whole lot of experience with that in Python, but I will say that it seems very easy to me, having looked at Flux now, to understand how that's possible. From a Python perspective, if I were using something like TensorFlow or PyTorch, I would not really have an idea what's going on, or could I even plug this in or not. So I guess to explain a little bit more, when you're training say like a neural network or some kind of model, there's a lot of differentiation that goes on during that training. So a big feature of FluxML is this automatic differentiation, and to do that, it's using Zygote.jl, which is a package specifically for automated differentiation, and it's got this gradient function which you can use to take gradients, and that it will handle any function that is differentiable, whether it's coming from Flux or whether it's coming from another library or whatever. So it really opens up a lot of opportunities to do stuff there. And then it's also got first-class GPU support. So if you've got it uses this CUDA.jl, and you can write GPU kernels directly using that, and will run on GPUs. It also works with CPUs. And then it can also be compiled for TPUs, the tensor processing unit. So lots of cool stuff. And it's got a large ecosystem, much larger than I realized when I first looked at it, of things that are like built on top of Flux, that are using Flux, or that can work with Flux. And on the website here, fluxml.ai, it's got a list of, well, here's like 6 big ones. There's, probabilistic programming using this Turing.jl, and geometric flux, which can do geometric deep learning, and all sorts of stuff. The SciML ecosystem, which is a big deal. In fact, I think the SciML conference is coming up in March, and that uses Flux and Zygote to mix neural nets with differential equations. So yeah, all sorts of really cool stuff. And there's a button here to see the entire ecosystem.
I think that I should probably mention that when you hear differential equations and neural networks, you have to remind yourself that the solution to a differential equation, you're essentially trying to solve for a function.
Mm-hmm.
And neural networks are function approximators.
Right.
And theoretically can model any function. There's a very famous theorem that proves this. So you can use neural nets to approximate the solutions to differential equations in a very black box kind of way, opposed to the heavy theoretical mathematics that's needed to solve some of these partial differential equations. So yeah,
right.
it's a really interesting field of study, though I don't know too much about it. I have friends that do it, and they seem to think that it's the new hot thing.
Gotcha. So Randy, when we started talking about this, or when we were kind of planning for this episode, you mentioned, you already had some experience with Flux, but maybe most of that experience was from a while ago. Is that
yes,
correct?
It was a while ago. So probably 2018 is when I was looking into Flux and another package that's no longer maintained called Tensorflow.jl. So these were the two packages that had YouTube videos out, and you know how I am with YouTube. If it's out there, I'll probably find it. So Flux and TensorFlow were the first ones that I saw. So they were the first packages that I started to learn. And back then, I wasn't as adept at programming as I am now. And it was difficult for me to read through the documentation back then in those early days. Now, the documentation has drastically gotten better, and it's easier for me to read, but still, there's a significant difference between how you and I learned to program.
Yeah.
I kind of beat my head around something, trying, looking at examples. And at the very last step, I go and I try to read the documentation on the website. And it's because I just don't really have that great of an attention span. And the state of it is better, but it's a lot. And when you and I started looking into Flux last week and over the weekend, I found myself getting confused a lot at first. And that's nothing bad about Flux. It's bad on me. I'm used to things like TensorFlow or PyTorch.
Yeah.
Transitioning to Flux from one of those frameworks is strange. And I've had a hard time trying to describe it to you over the phone when we've been talking. There's something distinctly different about the API for Flux that I couldn't put my finger on until maybe earlier this morning.
Okay.
Flux seems like it was written by mathematicians. And when I learned TensorFlow and PyTorch, as a mathematician, I had to start thinking like a computer scientist in a sense, and transition myself into that framework to understand their API. So that's where I was. And when I came to Flux, I completely forgot how I used to program before I started really diving into Python. I used to program how Flux is written because that's what I was at the time, just a pure mathematician.
Right.
So I'm going to go ahead and walk us through my first experience with Flux from a mature programmer perspective that I feel like I'm at now.
Okay.
So on my screen, I've opened up a Jupyter notebook that will demonstrate the basic functionalities of Flux in the context of a single neuron model. Okay, so a single neuron model is a supervised machine learning model that can be used for both regression and classification techniques. Before I elaborate on that, first, I'm going to create some test data and train data to use to illustrate what these things do. So I import Flux and I import plots and I set my theme to dark. That's my preferred theme for plots. And then I make a target function. which is equal to 4x plus 2. So it's just a very simple linear function. I define some training domain values of x and some testing values of x. Then I apply my target function to those values to get my y train and y tests, and then I scatter them, and we see points that would lie on a line.
Right.
And our goal will be to design a model that can learn the line that passes through these points using the training data, right? And the training data happens to be values 0 through 5, 0, 1, 2, 3, 4, and 5.
Yeah.
And the way that we're going to do this is with what I was mentioning earlier, the single neuron model. So altogether, this model consists of the following. We have labeled training data in the form of tuples. From a mathematics point of view, tuples, not a distinct x vector and a distinct y vector, tuples. And each tuple, the x value of that tuple is a feature vector, which contains the measurements, and the y value is the label. So in our case, the x value is a value between 0 and 5.
Yep.
And the y value is 2x plus 1, whatever the x is. So we're given this training data, and then we have a computational graph that resembles a biological neuron. This neuron, we have two circles called nodes that are to the left of the screen. And then from those two nodes, there are two arrows connecting them to a big fat node in the middle. And that node is split into two pieces, a Z part and an A part. These are called the pre-activation and the post-activation. And then to the right of this big fat node in the middle, we have an arrow pointing out to a value y hat. So the way that this works is an input signal is fed into the leftmost neuron, and a value of 1 is passed into the leftmost neuron on the bottom, because they're stacked on top of each other. And then those values or signals are passed through the edges, connecting them to the big neuron in the middle. And what this is meant to represent is that the signal is being multiplied by the weight on the first edge, and the value 1 is being multiplied by the value b, the bias, on the second edge. And this linear sum is passed into this big neuron in the middle. That's called the pre-activation value. The post-activation value takes that linear combination, in this case, w times x plus b, that's what's being fed into the neuron. The post-activation applies some activation function to that value, and we get to choose what that is. And the choice of that activation function will determine what we're trying to model, like what we can model, I mean. And then that post-activation value, which is equal to A, it's the activation function applied to the linear combination. It's spit out, and that's what we label y hat as our predicted label.
Right.
Now we have this prediction for a given input, we call it y hat. Next, we need a cost function to measure how well our y hat compares to what the y label should be. So the cost function is a function of the weight and the bias, because the weight and the bias determine the output once you've chosen your activation function. And I just have the average sum of the distances between our projected label versus the real label. Now, if this value is small, then our weights and biases are doing good at predicting the actual labels. Right? If the distance between our output and the true value in label form is small, then we're good. If it's big, it's bad. So picking a cost function is a way of giving us the ability to somehow train the weights and biases. And the way that we do that is with what's called gradient descent. But generally speaking, we have this idea. Tuples of labeled data, a single computational graph, a activation function, and a cost function, and then a way to minimize the cost function, because that makes the weights and biases better. So that's our model, and we have to look back to our problem. We have these scattered points in a single line. It looks like we want to find a regression line, a real valued line that passes through those points. So looking back to our single neuron model, we will choose our activation function to be the linear function. We're not going to do anything. In that case, A would be equal to Z. So our output is literally W times X plus B.
Right.
Now, this computational unit here, we can define with model equals to flux dot dense, capital D, and then parentheses 1, 1. What this is doing is creating a computational graph with one input and one output. And it automatically makes a bias term for you. You don't have to specify that. So the left input to dense is the number of features you're looking at, and the output is the number that you want to spit out. Once I've made this model, we can access the weight and bias by typing model.w and model.b respectively.
That's a capital W.
Yeah, capital W for the weights. So as I was mentioning earlier, the computational graph really is a function. Feed into it signals and it spits out something. And Flux treats it as such. Just type model, parentheses, and then throw in your measurements and it's going to spit out something. So for example, on my screen right now, I'm looking at the model applied to the XTrain array, and it spits out proposed values.
Right. Yeah. What you're saying is like, so this dense thing it's
a function.
Well, it's a mutable struct, really, is what it is, right? Like, and it's got the weights and bias fields, but then they've done like an overload on it to make it callable so that you can use it and it will return the, weight times X plus bias. So that was something I think coming from like TensorFlow and everything. Normally, like you create a model and then there's like a predict function.
Right, a predict method, right?
Or like a predict method. In this case, like the word model is like being used a little bit differently here than it is in like TensorFlow or PyTorch.
Yeah.
It's just that graph you were showing us, right? And so
right, it's just the computational graph. That's it.
Yeah.
It's a container for those weights and biases, and it's a function.
And it's a function. And so, you can pass a value into it or like a vector of values and it'll apply the function and give you the output.
Right. So this is different than TensorFlow. It really is, or even PyTorch.
Yeah.
Okay. So back to my single neuron model, the general structure, the data, the units, the activation function. The next thing was the cost function. So for linear regression, it's standard to pick the mean squared error function. And Flux has this function built in, and we can access it with flux.losses.mse. And we're going to define our own loss function using the MSE. And I have loss, parentheses, x comma y equals to, so I'm defining a function here. Mm-hmm. Flux.losses.mse, open parentheses, model x. So model is that computational graph we made earlier, and it's a function. So model x, if we pass in an x, it's going to spit out y hat, right? That's the proposed prediction. So MSE, open parentheses, model x in parentheses, comma y, the true value. So this is now my loss function, and I've defined it. Now, what else do we need? We need to train it somehow. We need to adjust the weights and biases to fit the data better. Mm-hmm. And the way that we're going to do this is in several steps. First, we need to define an optimizer. And for this simple example, I'm using the flux.descent optimizer. Now, I need to note that this is not stochastic gradient descent. That's what's typical when I think gradient descent. Flux.descent is the full gradient, meaning it's going to look at each of the data points in training and calculate the full gradient with respect to all of them, and then update the weights and biases.
Yeah, using this descent optimizer. You can customize all this if you want.
Right,
there's different optimizers, but this descent one is.
Right. Next, we have to format our data. And I actually really like this. We have data equals to an array, and then inside that array, we have a tuple. The left entry is XTrain, the Y entry is YTrain, or the right entry is YTrain. That's exactly how the mathematical formulation of the model is depicted above, and that's the way that I depict it.
Yeah.
So I like that a lot. And then next, we need to get the weights and biases from the computational graph to train on together with the cost function. The way that we're going to do this is with flux.params and then throw in your model. This will collect your weights and biases for training, and I assign them to the variable parameters. I'm currently ready to go. I can train now using the optimizer that I chose, which happened to be the descent optimizer.
Right.
So if I look at my loss before training, my loss was 127. And then I call flux.train bang, so .train exclamation mark. I pass in my loss, my parameters, my data, and my optimizer. So train bang is just going to apply that optimizer once on that data, on those parameters with that loss. And then I look at my new loss after calling that one time, and it's 120. So it went from 127 to 120. So the loss has gone down. Yep. Which means our weights and biases are performing better.
Yeah.
So what we can do is we can iterate this process over, say, 1,000 epochs. And an epoch is just a iteration of this descent method. right? One iteration of this descent method. And in the code in front of me, I change it to implement what's called stochastic gradient descent. So for epoch in 1 to 1000, I pick a random index called I. So I is equal to rand 1 to capital N, where that's the number of data points. And then I call flux.train bang on the loss, the parameters, and then the ith data point. So it's like randomly picking out one of those data points, and it's applying gradient descent on just that one point. And I do this 1,000 times. This would be stochastic gradient descent. And we see that the old loss was 120 and the new loss is nothing.
Yeah, 1.4 to the negative times 10 to the negative ninth.
Right. So then if I wanted to plot my line, there's several ways to do this. I just happen to make a domain and use my weights and my biases to plot that domain against the test points. And I see a line in front of me that passes through each line perfectly.
Yeah. So the line is the predicted values.
Right. That line was learned using the data 1 through 5.
Right.
And it's passing through the points 6 through 10.
Right. Yeah.
That's the cool part about machine learning.
Yeah.
So this is just a pretty cool example. And it was really simple to do.
Yeah. I do like this example, especially because it's just so easy. You can actually go. So I think the original function was what, like 4x plus 2?
Yeah, it was 4x plus 2.
Yeah. So now that you've trained your model and everything, you could look at those parameters, the weight and the bias, and they'll be really like the weight will be very close to 4 and the bias will be really close to 2. So you can see that it
will be essentially the 4 and 2. Right. So, and that's awesome. And single neurons and neural networks are great function approximators. That's what they're made to do.
Right. One thing I wanted to just kind of mention about this example real quick before we move on, what I really like about it, is that it really lays out the entire process. And as you look at more and more examples, you realize that it's all just this process. Everything kind of like follows these exact same steps. It can get more complex in terms of what's happening at each step, or like, you can create more complex computational
graphs
and everything.
Yeah.
And all sorts of, and it can be fully customized. But this really is like, this is the template and everything follows this. It's so easy that I could imagine teaching machine learning, like an introductory machine learning course, and jumping into the code at the same time that you're teaching the theory with using Flux, because it mimics everything so much. Whereas could you maybe you have experience with this, but I was trying to imagine like, what would it be like if we're like, okay, here's our introduction to machine learning class. It's theoretical. On the one hand, we're learning the theory, but then we're also going to be doing it, say, using something like TensorFlow and Python.
My course at Rice is exactly that. It's a 3-hour course because it's once a week. The first half of the course is the theory. The second half of the course is programming it from scratch.
Yeah.
So it would be easier to use Flux in that case.
Because it seems like you could, with Python, it'd be like, okay, we're going to teach the theory. And then there's like almost a whole lecture on like converting that to like, okay, here's how you do it in TensorFlow and how things kind of map to each other. And, oh, this is being taken care of for you behind the scenes. And there's like this steeper learning curve to just understanding what TensorFlow is doing.
There's more hidden. There's more hidden in TensorFlow.
There's more hidden.
And there's more hidden in scikit-learn. It's hidden there, right?
Yeah.
Whereas in Flux, everything is explicit.
Yeah, it's very transparent. Yeah.
The training might be hidden, but the model itself, building the model, is exactly as it should be.
Even the training isn't actually that hidden. So like, okay, yeah, there's this train function and like maybe you don't know exactly what's going on, but you could just go look at it like in the source and it's all written in Julia. And my guess is that it's really simple. Like my guess is that it looks exactly like what it looks like when you write it out mathematically for training.
I think if Zygote so Flux has access to the gradient function from Zygote, correct?
I'm not sure if gradient is from Zygote, but yeah, it's using Zygote.jl.
In my for loop for my epochs where I'm training, I think, and I'm going to try this later, explicitly write out gradient descent, right? The computational graph is a function, the gradient function from Flux or Zygote, wherever it belongs, can calculate gradients of that computational graph. So I really could say something like W minus equals a learning rate times gradient of the model at that point.
So actually, there's an example on on the website.
Did that make sense though, what I was saying?
Yes, absolutely. And I think they've done exactly that here. So on the Flux documentation website, there is a section called Basics. And inside of that, there's like an article called Taking Gradients. And it talks about using this gradient function to take gradients, and the whole automatic differentiation, which is really interesting. And it mentions like, okay, here's an example of a function with two parameters, right, that we could take a gradient of. And what does that function look like? It's looking a lot like what would be part of the mean squared error, right? And there's an example of, building a simple model where you start with a variable called W, and it's just a random 2x5 matrix. And then you've got a variable B. So this is like a 2x1 vector. But you can see, okay, so here, instead of using like the dense layer, so you could make you could sort of mimic what this dense layer is doing, as it's just a function here. They've named it predict. It takes one argument X and it returns W times X plus B. And then here they've defined the loss function explicitly using you first compute your predicted value using the predict function, and then you return this sum.
Notice on the screen, sum of y dot minus y hat. That was what I had on my slide earlier. It's
right,
exactly.
Yeah, exact same thing. So this is they're creating their own. It's not quite the mean squared error, but it's like a simple version of that. Yeah. And then you can say, okay, for some random X and Y values, what is my loss at? And then here's where they're showing you how you actually compute the gradient. So what this gradient does, it uses the gradient function, and it's going to take the parameters, so the W and B, and then use your loss function to in the gradient. So it's taking the gradient on the loss function basically with these parameters. And now that you've got the gradients, then here it is. You can just update your weight.
That's what I was saying earlier. W minus equals some.
I know, exactly.
Learning rate times W.
So it's all actually written for Scratch here, and it's like, I don't know, a dozen lines of code, if that even. And it's so simple, and it just looks like what you would see in a textbook.
Yeah.
Which I feel like is something we repeat a lot on this podcast. So it's like, man, it looks like what I see in the textbooks. So yeah, really, really cool. And you're right. Like you could implement all this stuff from scratch, and it's actually not that hard. Like it's very easy. If you understand the theory and a little bit of Julia syntax, like you can implement this stuff pretty quickly. Again, I just really like how I find myself saying this all the time with stuff in Julia as I'm learning it, is that it just seems to fit into my brain better than some of the stuff coming from Python. At some point you use TensorFlow, PyTorch, whatever enough, it starts to fit in your brain because you've sort of, molded your brain around it. But it feels maybe unnatural at first. Whereas this, like you mentioned, it felt maybe unnatural at first because you were coming to it from, with certain expectations that you had from working with like TensorFlow or something. But really, it's much more natural. And I just love that. Like you said, so much of it is just like, well, if it doesn't have what I want, or if you're trying to implement something and you're not sure how to do it, just write the equation the way it looks. It'll work.
It has the feeling of programming these algorithms from scratch, but is giving functionality to get rid of some of the annoying points of doing it from scratch.
Yeah.
Like it's helping with those annoying points, but it still feels like doing it from scratch. And all of these things I program in Scratch when I lecture on these topics in Python, because programming it from scratch matches the textbook or my notes definition of what you should do. Right. And this here matches that as well. If I were to try to use something like scikit-learn or TensorFlow, it does not match my notes. There's an extra learning step that you have to cover before you can dive into those things.
Right, exactly.
So yeah. I think the Flux is a beautiful API for having the appropriate amount of from scratch feeling and functionality.
Yeah, and it's always because machine learning is like one of these fields, right? That it's growing and changing all the time. And yeah, there's a lot of sort of standard models out there, maybe for certain things, or these like components. But really, when you're confronted with a real world problem, there is almost zero chance that there's just a model that you can just use, unless it's like a solved problem or like a problem that a lot of people have worked on. But if it's a brand new problem and you're one of like a handful of people that are working on this problem, you're trying to build a model for it, chances are you're going to have to do some kind of customization, and that can be very difficult to do in TensorFlow or in PyTorch, or at least
it's non-trivial. You have to subclass things, you have to
it's not just writing Python code. You have to understand more about the way the library works, like how TensorFlow works or how PyTorch works. And there can be very like radically different ways that that's done on like the internals of the library. Whereas with Flux, you just write Julia code. If you know how to write Julia code, you can customize Flux to your heart's content. So that's another thing that I think I really love about it, having spent some time with it. So it really, like you said, it's kind of this really nice balance between it's taking care of some of the more painful aspects for you, and it's got, you know, all your lost functions, and it's got things like that, some common activation functions.
It has one hot encoding that we'll see next week. It has these things that that are annoying to do from scratch, but aren't necessary to match the theory.
Right. Yeah. And so then you can really build and customize. And then of course it takes, or you have to take into account all the optimization that happens with Julia and everything. So what you end up with is kind of like my thoughts on this. You end up with something that looks just like what you would see in a textbook, including like the math and everything, making it a really good, you know, potentially a really good teaching tool for teaching a machine learning class, but you don't sacrifice any performance. So at the end of the lecture, your students have implemented maybe some simple model or something. Well, they already know then how to write good Flux code. Right.
And can generalize it to other models. For example, this same type of code we could generalize to the perceptron algorithm, which is just a different sign function. The same type of code could be generalized to support vector machines.
Yeah, it's super cool. Well, I want to mention a couple of cool things I saw about Flux as I was looking over some stuff this past week. There is a blog on the fluxml.ai website, and one of I think it's the most recent entry, at least at the time we're recording this, is about Flux becoming a part of the NumFOCUS, or partnering with NumFOCUS as an affiliated project. So NumFOCUS is this organization that sponsor projects. They have affiliated projects and everything, and there's quite a few in their ecosystem. So there's a lot of Python stuff and R and, you know, all sorts of stuff. But for example, NumPy and Matplotlib and Pandas and Jupyter and IPython and Cypher, and like almost the entire Python scientific stack is part of this NumFOCUS. And so Julia itself, the language, I believe is part of NumFOCUS. And then as of December 2021, now Flux is also included in that. And that's really
cool. Awesome.
Because it opens up a lot of nice things for them in terms of like, you know, funding and access to resources. You know, they say here, you know, the partnership will help them grow the community, bring new contributors into the ecosystem, and manage funds and future grants as they grow and continue everything. So I think like NumFOCUS can, you know, it'll help them with grant proposals and things like that. So that's really exciting because that can only mean good things for the future of Flux, I would think, right? Like it's going to continue to be maintained. It's going to continue to grow and probably have wider adoption as well as a result of just having, you know, more resources available to them. So that's really cool. I was really nice to see that. And that's relatively recent, just within the last couple of months. But as far as just, you know, where to go next with Flux, like next steps, I kind of felt like, you know, there's this fluxml.ai website and it's got some tutorials and stuff on there. I found that I preferred looking at the tutorials just in the documentation itself. So on the fluxml.ai website, there is a link to the docs up in the navigation menu, and that'll take you straight there. Right on the homepage, it talks about, you know, how to install it and then how to learn Flux. And there's a link to this overview article. And we kind of went through that today, but that was where I started and was really happy with that. And then just going through, I would say, you know, the documentation is good, and just working through this whole overview section and then the basic section really gets you quite far into understanding how it all works. Right. That would be my recommendation of starting there. And then another thing that was really nice is they've got a model zoo, and that is a GitHub repository with a ton of examples of models. So if you just want to dive in and see like, okay, how are you building models? How are you doing things? There are tons of things to look at here. Yeah, there's a list of all the examples. So they've got like computer vision, working with text. That's, I think, a good resource to just look and see, some examples.
We should probably note, though, that some of the code seems outdated or deprecated. Some of these examples are older, and just be aware of that.
Yeah, that's
when
a
you're
good
going
point.
through them.
That's
Which I would actually love to contribute to these models. I would love to do that because
Oh, you should.
I write notebooks all the time for students learning how to do things. So I would love that.
I'm sure they'd appreciate some contribution. So you should totally do that. Yeah, there is maybe some stuff that's outdated, and that is something we should also just mention, is that Flux is not, from what I can tell, like it's not at a version 1.0 or anything like that. I think it's 0.12 or 0.13, or I forget the exact version that I was looking at. But if you go back even just a few versions, there's been a lot of changes to the API. So it's still, maybe it hasn't reached that maturity and that stability in terms of the API and everything yet, but it seems like they're getting there. And now that with the NumFOCUS stuff, like they should get there soon, and then it'll really be something that I think people will be excited to start adopting.
All right. Well, I think we should mention what we're doing next week, and that'll be it. So next week, we're continuing our dive into Flux. There's a lot that you can do with it, and we can only cover so much today.
Yeah.
Next week, we will look at deep neural networks, and we're going to implement this on this famous Amos data set. And then also, I plan on looking into maybe some recurrent neural networks or convolution neural networks, because now that I'm starting to understand the API more, it seems to be the case that implementing those things will be very easy and pleasurable to do. So awesome. I'm excited about next week.
Well, Randy, thanks for hanging out and talking Julia with me again this week.
Yep, it's always fun.
All right. See you next week.
Later.
Take care.